I'll be talking about how should we think in terms of how a table of concepts might form over time. So the world throws at us sights and sounds, and we try to make sense out of these sights and sounds and find patterns so that we can predict what might happen in future or what actions to take. And what is the main algorithm that we're using here? What could be the block diagram of the architecture from an algorithmic viewpoint? Is it modular? Is it even using deep learning? Now, do we have memory, a table of memory where we store concepts? Now, there is this ancient mnemonic called the tabula rasa, which says that we are born with an empty slate in our mind, and as we go through experiences in life, we form concepts and notions and beliefs, and that's what helps us deal with the world. So, is there such a table? So, thinking about a table of concepts allows us to think of deep networks in a modular fashion. So this is useful because we can now things become more interpretable. For example, if you experience some event, then you can interpret it as the set of modules that fired and the order in which it was fired, and that gives you some very simpler way to look at that event. But I believe that modularity is useful not just for interpretability and to make sense, but it's also important to actually learn very high-level abstractions with a small sample complexity. So it's not just efficiency that matters here. So let's just think about how might we store experiences. So let's say you just meet someone for chat over coffee. Then how are we remembering this event? Who did we meet? What did we talk about? What was the setting? How many other people were there? How do we represent it? And more importantly, how do we index it? And if we meet that person again, how do we recall this event? Is there some kind of a knowledge graph that we build in our mind? And I want to emphasize that here we are not trying to understand exactly how the human brain or the mind does it, but what is the essential ingredients of the algorithm or the algorithmic architecture that we have. So this is not a physiological study. It's a study of the algorithmic architecture. So if we close our eyes, we can actually recall events from the past, sights, sounds, which means that we must be storing some kind of a sketch or a caricature of that event that can be used to approximately reconstruct those images or that event at some level. Another thing to note about our memory is we tend to forget very gradually. That is, we don't forget things all of a sudden. Maybe I might forget the fine details of a conversation, but I might still remember very high-level information like the topic that was discussed, and I might not remember all the people who were there in the meeting, but maybe I might roughly remember the main people I interacted with, or roughly how many people were there. So maybe if we just think of this as a thought experiment, then maybe in our mind we have a modular network. So for example, in a chat with someone, maybe in our mind we have a module for person recognition and a module for speech analysis. So, and there could be many, many other modules. Like you can have modules for math, for driving, or for other activities. But at a time, only maybe a small number of modules is firing. So in the conversation, only the person representation module is firing, and the speech representation module is firing. And we are trying to, the subset of modules which fire essentially captures that event. So at an abstract logical level, we can think that in our mind there's a set of modules. Of course, it's a big difficult question as to how do we even form such modules? Is it actually physically separate modules? But let's ignore that for now. Let's assume that we are born with some initial set of modules, and we'll see how that could be useful in maintaining a modular structure. So any event will probably just fire a small set of modules, and there is a certain skeleton of a DAG if you chase those firings. So, and every module is producing some embedding representation of whatever it finds. So when we want to remember an event, we can just remember it simply as the skeleton DAG that fired along with the vectors that were flowing along the edges of this DAG. So it's relatively easy to store this DAG and the set of firing vectors along these edges. And here is a very simple way to do it. You can just take the DAG and the firing values, and you can somehow map it to a dense vector. And the dense vector is sufficient to, from the dense vector, you can actually tell which modules fired with what values. And to see that, just look at one flat hierarchy of modules. So let's say you have thousands of modules in your mind, and only, say, a couple of modules are firing, like the person recognition module and the speech analysis module. So you can just, you want to remember which modules fired and the vectors that came out of those. All the others are producing 0 vectors or not firing. So you just do simple subspace encoding. That is, you just map the output of each module into a separate subspace. And if you do that, it's simply a linear transform, which means that you have a separate rotation matrix that takes the output of a module and packs it in some subspace, in a different subspace, and you just add them up. And you need to make sure that the output, and you get a single sketch for this event. So you need to make sure that the dimensionality of the sketch is more than the dimensionality of each individual output. So if let's say k modules are firing here, each of dimensionality d, then the sketch better have like a little more than kd dimensions in it to make sure that it preserves all the information about the sparse set of modules that fired. So maybe like if you have like kd log n, where n is the total number of modules, that's fairly enough to recover back the exact set of modules which fired. And this is the reason you can do this is because you can just use sparse recovery. You know that the final signal is a sparse combination of things in certain subspaces, and that's why you can get back the set of things. So one trivial way of doing this is you just look at the final sketch and multiply it with Ri inverse. And if R is a random matrix, then you can just multiply with Ri transpose. So if you multiply with Ri transpose, then those subspaces which have firings in them, they will stand out and have a high norm. But any subspace or module which did not fire will have a very small norm. So you just keep those Ri transpose multiplications which have a high norm, and that'll tell you which modules fired and with what values. So it's exactly like creating a sketch where there are a lot of component sketches in there, as long as the number of components is small. And every component is, you can think of a different type. So you can recover, it's like an object, and you have, the object is a compound type, and it has certain component objects, and then you can, each one is a different type, and you can recover the type of it, and you have pointers to those objects. So as I said, this is exactly like sparse recovery. And in fact, even if you did not know these RIs, to be able to take multiplied with Ri transpose, you can actually treat it as a dictionary learning problem. So if you see lots of sparse combinations of these different module firings, then just by using dictionary learning, you can actually figure out these RIs. So in dictionary learning, you just have individual, the xi's are actually scalars, where either the xi is 0 or not. Here is the xi's vector, so it's a slight generalization of dictionary learning. But the same principle applies. It's the same generalization of sparse encoding and dictionary learning. By the way, if anyone has any questions in the middle, I'm perfectly happy to be interrupted and take questions. So this can be used to construct a sketch when all the modules are in one layer and only a small subset is firing. But the same idea can be applied when you have modules in different layers and you have a hierarchy of such modules. The way to extend it is very simple. You just recurse in the sense that when you are taking the output of a module, you don't just put the output vector of that module, but you also recursively compute the sketch of the modules before that fed into it, and you append that into this X2. So when you do that, then when you do the decoding and you find X2, then in X2 you have got the output of the module 2 itself, but you also have got the recursive sketch of the modules that fed into the module 2. And then you can just keep recursing downwards and you can construct the DAG. Yes, hi. Hi, Rina.
Isn't the model equivalent to simply concatenating all of the R's into a single dictionary, concatenating all of the X's into a single vector, and then requiring block sparsity in the sense that...
Essentially, yeah. The actual thing is a little more complicated. So to get certain guarantees, certain kinds of provable properties, you need the RIs to be have a certain structure. Like it's not a random matrix, it's actually identity plus a random matrix, and there's some further additional block structures in there. But essentially, but at a high level, what you're saying is correct.
And what is the reason for requiring the R sub i's to be rotations?
Yeah, they don't have to be. I'm just saying that even if they were just rotation, actually, these are not square matrices. These are like rectangular matrices because naturally the output dimension has to have enough dimensions to pack a couple of these xi's, which are non-zero. So why is it rotations? No, they don't have rotations. Just rotations also works. So you could do something more complicated.
Thanks.
So you can build a recursive sketch that can be used to encode a DAG of firings, a DAG of firings in this way. And it gives you a dense representation of this DAG, and you can decode it to get back the original DAG of firings, as long as the DAG is small and sparse. So what this does is it constructs one uniform sketch space, and you have concepts or representations of events in this sketch space in such a way that events that are similar will tend to get sketches in related directions, and which are very different, they won't have things in the same direction. And for example, if you have a meeting with some person on some topic, then the sketch of that compound event, which is the meeting with the conversation and the person, that sketch will be related to the sketch of that person, and it also will be related to the sketch of that topic. And the reason it will be related is because one thing as I mentioned, these RIs are not random with mean zero, but actually it is identity shifted, so identity plus random. So if you make it identity plus random, then what will come out is if x1 and x2 are the non-zero, the first two modules are the non-zero things which are firing, and the other is zero, then just x1 times identity plus x2 times identity will bring the sum x1 plus x2 in the sketch, and plus the random rotations. So that's why the compound sketch, which involves x1 and x2, will actually be correlated with the individual objects of x1 and x2. So, which means that this meeting, a compound event, you'll be able to reference it into the individual component sketches. And also, when you have subtypes, like you have animals as a class, and then you have different animals within that, those subtypes could be subclusters. So all the animals might form a cluster in the sketch space, and separate animals might form subclusters within there. Because maybe you have some animal module that is firing something, and then you see that when animals of the same type are seen, then they all become you get sketches of the same type, and that's why you notice subclusters in there. And this can be used to also infer new concepts by noticing new clusters arising. So up to a certain level of abstraction, if you've already formed a library of modules, then the way you notice a new concept is because whatever representation comes out of these new modules, if you see a new cluster arising in a region which has not been seen before, then you know it's time to allocate a new module and train things about that thing. So, if you've not seen a tiger before, then maybe the representation that comes out of the animal module, you'll see a new cluster, and now it is time to train things what to do when you see a tiger. Like you're training yourself to run away, or you're training yourself to remember the patterns in the images of a tiger. So so it gives rise to this picture where these sketches form a knowledge graph. So over time, as you go through events, then you'll keep accumulating sketches over time in your life, and they will reference each other based on their relations, and you essentially form a knowledge graph among these sketches. And these sketches are constantly interacting with the modular structure where a sketch is formed based, so when you meet someone over coffee, then you see that sketch, and you put it into this repository of sketches. And when you meet the same person again, you retrieve, you meet the same person again and talk about the same topic, then you get a sketch which is similar to the old sketch. So you'll go back to your database of sketches, and you'll retrieve that, and that will inform the conversation that you're continuing with that person. So here are some provable properties that you can show about this method. So one thing is, it's possible to prove that if you choose these matrices appropriately, then it has the similarity preserving property, in the sense that if you have related events where almost the same set of modules are firing with similar values, then you will get same sketches, just because of the way you are composing things into a sketch. So it gives you this knowledge, a graph structure over these sketches, where related events have similar sketches. And also it has this graceful erasure property that we talked about, in the sense that you will not forget things suddenly. Because it is packing a sketch, an output into a higher dimensional space, so it's taking from d dimensions to, let's say, k times d dimensions. So there's a lot of redundancy in this. So as you forget half the dimensions, you might still be able to recover the outputs. So if you have many outputs from different modules, and especially if you weight them, you give higher weight to the important ones and lower weight to the less important ones, then as you remove half the dimensions, you might still be able to recover the higher weighted ones, and you might forget the lower weighted ones. But even if you forget the lower weighted ones, it doesn't mean you forget everything. Like you might still remember some aggregated properties about them. Like you might still remember the average values or the variances. So if you have, like in a room full with hundreds of people, and if you have a small sketch whose size is not 100 times the representation for each person, you still get things like averages like, okay, what are the typical height of the person? Were most of them wearing dark shirts? And the reason you can get that is because just look at this, the way the sketch is computed. If you have hundreds of things firing, and if each Ri is I plus a random thing, then this sum, with the average value here, will be very close to the average value of all the firings of the different outputs. And you can also get other higher order averages, like the second order moments and third order moments. And the way you would do that is, instead of just taking Ri times x, you could just apply a nonlinearity on these Ri times x and then add them up. So when you add a nonlinearity, then essentially what you're doing is you are not just storing Ri times x, but you're also storing higher powers of it. So you're storing things which have the squares of x, the x, x transpose x, and then the third order, and so on and so forth. So when you take averages, you can get things like this, the first order average and second order variances and so on and so forth. So, yeah, so you can get this kind of average, and it has this interpretability property. You can get counts. It's like how many people, roughly how many people were in the room. It also allows you to think about this in an object-oriented fashion, in the sense that you are composing objects into a structure and being able to decompose them. It gives you a protocol-independent way of communicating between modules. So normally in computer systems, when we communicate, we have to really agree, the compiler has to agree on how classes and their fields are stored, at what offsets they're stored. But here, this is one method, by just this random subspace packing or things of this sort. It essentially lets you communicate in a way where you're not fixing this protocol a priori. You also have this ability to view things in terms of pointers. So for example, you can have a sketch, compound sketch of many things, and from there you can recover the original sketches, or at least some hash of it. So those hashes could be used as pointers. So maybe the actual component sketches are very big. So you're not able to recover it fully from this final sketch. But if you have stored them in your sketch repository, then just the hash of it is enough to point it back and to bring out the original thing. So if we actually think further into this thought experiment, then the picture it gives rise in terms of how sketches are forming and how modules are forming is something like this, where you have external phenomena which is throwing in images and sounds, and then you have this table of sketches, and you can use some similarity preserving method like LSH or some other thing to index into it and retrieve out of it. And this table of sketches this table serves both two functions. One is to store sketches of external events, but also to store modules that are trained for different types of phenomena. Because as I said, when you are learning a new concept, all you're doing is you're hashing into a region of this sketch space, which was initially empty or initially had a very low access count. So when you start hitting a bucket where the access count is very high, it's time to allocate a new module. So at that every entry, essentially you just have a module. So it's like, for seeing a tiger, then you are seeing a new bucket and you just train a small network to deal with this new phenomena. And there is this routing module which takes external phenomena or a sketch coming from the previously executed modules, and then decides where to index into this hash space, sketch space. So it's an iterative loop where you are constantly accessing some modules in the bucket. You're hashing into a bucket. You're finding modules to execute. You execute those. Those produce new sketches, and it comes back to the routing module. And you combine those sketches in some way, and you decide now a new location to go into this bucket and get new modules, and I keep executing. So it's like an iterative modular loop here. And the routing module is probably complicated. It's not just taking a sketch and it's not taking some output sketch from previous thing and just directly hashing it out, directly indexing into this thing in the next iteration by just doing some softmax. But it's probably doing things like taking a sketch and removing parts which are noisy and keeping the parts which are stable. So for example, if I see the sketch of a face, then I need to remove things like the orientation of the face or specific lighting conditions and keep the more stable parts before I look up this thing. And also I might need to combine sketches. So if in one iteration, you might not just execute one module, but you might index into a few modules and you get some output sketches, and you might combine them in specific ways, and then produce the new set of indices to look into. And there is probably also a graph structure in across these modules, across these hash entries. And the reason you might have a graph structure is if you see two sketches which are constantly co-occurring, then you might want to think of those two as, create an association between them. So if I see two people are always together, and whenever I meet them, he's always another person, then you want to create an edge between them, or you want to create a compound sketch which captures both of them, and store that, which will reference to both of them. Or if I always see eyes with nose and mouth, then I want to create some association between the bucket entries for those, so that if I just see eyes and nose, I know that I can anticipate a mouth. So as I said, a new concept is just the constant access indexing into a bucket, which had a frequency of 0 earlier, and now it's getting a high frequency. And that's how you allocate a new bucket, allocate a new concept, and you have a knowledge graph structure on this based on co-referencing or association. Any questions? Yeah.
This question of determining whether a new concept has been discovered appears easy to explain, but the implementation of it is, I would argue, non-trivial because, well, first of all, what is, if I've never seen the concept, why is it new? And then how do I determine that I have, what is the computational implementation of popular, that I have sufficiently many new? In principle, I could just set a bunch of thresholds and numbers, but that's not going to generalize across a rich variety of concepts. And in particular, also, it depends on the level of semantic resolution, because say if the concept is face, and I didn't know what a face is, but eventually I might want to recognize your face versus another face. Yep. And so how do you implement all of this?
Yeah, so I agree. This is a very, very high level. We'll see some details of it for specific class of images. But I agree this is very sketchy. But some points I want to address into a question is, so you don't want, the clusters may not be just Gaussian clusters of uniform radius in all directions, but it might be a subspace. And that's why the routing module has a very important task of figuring out how to orient sketches or compounds or sketch combinations to remove the parts which are variable and keep the directions which are fixed, and only use those for indexing, so that you get very, distinct tiny regions that map into buckets. So when you have faces, all human faces, it's a cluster provided you remove those directions which are variable across different people. So that's the job of the routing module. Now, when you look at individual faces, then they are further subclusters in that all faces subspace. So it is probably much easier to do that. That is, when you take the sketches of same person to figure out what to remove and what not to remove to point out the single cluster for a person, is probably a much easier task than identifying that single subspace across all people, the face recognition, the face detection problem. So this is another view that comes out from that architecture, is that you have a graph across these modules, because the modules are sitting in these hash buckets, and you're constantly, through the loop, you are constantly accessing one module, and then that spits out some sketch, which lets you go to another module, and so on and so forth. You get a path like this. And you might be have many such parallel paths, like a few such parallel paths. So you always have a couple of or case of sketches in parallel. And the paths could merge, you could shuffle the sketches and get new forks. And also, you might have these associations that I was telling about, the chaining of sketches across the buckets is a very important, I think it's a very important thing, because that could lead to long chains in memory that are very frequently accessed. So for example, if you're cooking a dish, then there's this chain of always, taking a pan, heating it up, and then chopping the vegetables, and some specific set of things which are very commonly accessed. So even when you're learning a new dish, to cook a new dish, based on the context, you might go to a bucket and you might see that, okay, there is this frequently accessed chain of events which have high frequency associations. And so you retrieve those and then you adapt it to your new task of cooking the new dish. Some of these edges could be static, some could be dynamic. So these edges could be hardened associations, but they can also be dynamic based on the execution of a previous module. So for example, if you're doing a math problem where you're trying to solve an integral, then you don't know what is the next module I'll apply, but I will actually do some steps, some maybe integration by parts, and then that tells me that now I have to apply this next step based on what comes out of the previous module. So they're both static and dynamic links here. And when from a human psychology perspective, when we are thinking through a chain of thoughts, then it looks a little bit like that because we have a thought at a moment and then we execute the thought, and that gives rise to produces the new thought that we then execute. And maybe we can abstract out execution of a thought as looking at the sketches in that thought, component sketches, accessing the modules that are related to those sketches, and then executing the modules and producing a new set of sketches, which forms a new thought. And now look at this, this becomes very similar to transformers in the following sense. So transformers do take a set of sketches, we call them tokens, and it takes different subsets of those by combining them based on attention, and then it runs a feed-forward module on each of these combinations, which produces a new set of sketches, which is a new set of token representations. And you can also think of this as a generalized decision tree or a decision graph, where the nodes of the graph are not just boundary decisions, but they're actually modules. So you get a graph over modules. Any questions? So let's compare this with today's transformer architectures. There's a lot of similarity here. There are a lot of architectures today which do combine transformers with some external table of knowledge. For example, you augment transformers with like a table of entities or a table of mentions, and either at the initial layer or once in a while in the middle, you look up which entity, some entities or previous mentions, you retrieve those based on output embeddings, and then you use those. There's also this mixture of experts where instead of a single feed-forward layer, you have many modules there. And based on what comes from the previous layer, you route it to one of the experts. So that is also very similar to what I was the picture I was showing in the last few slides. But one difference is that it treats this table of entities and mentions. It views this very differently from a table of computational modules, which is the table of feed-forward layers. And there is no real reason to view them differently because they are all ultimately using the same routing property, routing function, that is just routing the previously obtained sketches or previously obtained embeddings, and deciding which entry here to go to or which expert to go to. So really you should co-locate these computational modules and the stored sketches, which is exactly what I was mentioning here, that these buckets are storing both sketches and modules. So, and another thing that is missing is the graph structure within these experts on these entities. I think that graph structure is very important. It's important to keep the associations, figure out common paths in those graph structure, and then condense those paths into a new compound subroutines or compound modules that call these individual modules. And you might also want to have this routing table, this routing module. It probably needs to have a stack so that it can make recursive calls. So if you get a set of sketches, like tokens in a sentence, you might want to group them into a few sets, like a couple of subsets, and then recursively call modules for each of them, and then combine the answers. It's like Just like we used to do stack thinking, right? When I have a problem and I use divide and conquer, I break it up into components and I run each one separately and then I combine the results. You might also need RL exploration in deciding these routing actions. So today they use just softmax routing. So they don't explore, let me try out different paths and see which paths, some kind of policy that could be beneficial. So I think that is a very important component. That could be a very important component in having the right ideal router design. So reality is far from, so today's MOE, today's modular, whatever sense of modularity we have in the state of the art, I think is probably far from the true richness that should be there in the design of modularity and in the routing components. And we don't at all see clear semantic DAG-like representations. So it's not like when I see a situation, I can really mark it out as distinct concepts with the right relationships between them. So let's talk a little bit more specifically into this DAG-like representations. What is the exact function of these modules? Ideally, the exact function of these modules is to create nice semantic DAG-like representations that were generating these inputs. So let's just talk about images, and let's talk about cartoon images. And cartoon images are nice because we know that they are generated using simple DAG-like representations using some graphics package. And reality, real things are messy because we don't know if it's completely possible. But maybe what we do, what our minds does is when we get a real situation, we just use the approximate cartoon-like situation that matches this one, and whatever DAG that, we just use that DAG corresponding to that cartoon-like situation. So that's one advantage of theoretically studying these cartoon-like images. So take, for example, this one. There's probably a relatively simple DAG structure in the program that generated this. So maybe there was an object or a node for each individual thing, and for each individual thing, it was composed by using like a head-like shape and with the dress-like thing and the shoes, and then combined together to produce one of them, and then two of them are produced, and then overlaid together with a handshake. So the task of our system is to actually to reconstruct back this DAG or something equivalent to that. So let's see some more details about how to discover concepts in these kind of cartoon images, and particularly in arising of concepts of different kinds of shapes in these images. So for cartoon-like images, here are two very simple building blocks that maybe these are some of the most important building blocks in these DAGs. So these DAGs are like the nodes are functions. They're not just plus operators. They're not ReLUs. The nodes are actually function compositions. So one particular important function might be a polynomial function or a polynomial threshold function. So for example, using polynomial threshold functions, you can generate shapes like ellipses, or using intersections of polynomial threshold functions, you can generate these kinds of things like rectangles and cylinders. And by unioning these, you can build cartoon-like stick figures. Another important one is low-rank products, which can be very useful in finding repeated structures. Like if you have a sequence of birds flying, then you're essentially taking the latent parameters of one bird and then just changing the position in an arithmetic progression. So it has a natural low-rank product in generating this image. And specifically, you can view the image as a map from pixel position to a color. And we are trying to generate the DAG or some representation that produces this image. So for example, there might be some DAG So just if the image is actually a smooth image, then there's probably a simple polynomial, low degree polynomial that produces that image. So that function will be given by that figure on the right. You're just trying to discover the polynomial. That polynomial is a very good representation of that image. If it is a PTF, then it is just a polynomial with a threshold. So the image of an ellipse can easily be represented by that. If it is a rectangle or a cylinder, then it is a product of polynomial threshold functions, because the rectangle is just the product of the PTFs corresponding to the 4 edges. A cylinder is just the product of the PTF corresponding to the circular surface and the 2 things on the other sides. And then you can have a sum of products or a union of intersections to generate something like this stick figure of a man, and some more such complicated things to get that minions image. So the question then becomes, can we, by looking at the image, can we figure out that polynomials and the set of polynomials, the coefficients and the order in which they were intersected and unionized to produce that image? And as I said, the low rank products is another very important operator in this DAG, besides the polynomial threshold functions. So even just texture, when you have an image, an object with certain texture, that is exactly a low rank product, because you can just remove the texture and represent a monochromatic image, which is just a 0 or 1, and then putting the texture is the same as crossing that binary 0-1 image with a texture vector that is multiplied everywhere. Same with motion. Motion also can be thought of as taking the description of an object and taking the motion parameters, like the position parameters, and then crossing it out so that you have many copies of that object at different positions. And the low rank representation is a little more general than just the standard one, because first of all, the multiply operation could have some nonlinearities, especially something, it should include like convolutions or Cartesian products rather than just pure multiplication, the matrix multiplication products. And the plus also might need to be a little more general, like it should include occlusion so that you're not just adding 2 images, but you're occluding the parts where they overlap. So here is a simple DAG that you get just by composing PTFs and such convolutions or low-rank products. So if you have an image of a bouncing ball, like a red ball that is bouncing this way, then you have one polynomial that's describing how the center is moving. So that polynomial is a union of parabolas. Okay? And the base object, the red ball itself, is a PTF, is a polynomial threshold function, which is given by the circle thing. And you are now multiplying it with the texture, which is the color, red color. So the entire video of the ball can be obtained by just composing the circle is given by a PTF, but it is parameterized by the centers of the circle, which is a free variable. And you're binding that with whatever comes out of the motion, and you're feeding that. And that is how you're changing the position of the circle. So in the end, the entire video can be written as this kind of product and composition. So it can be thought of as some nonlinear operator on the Cartesian product of the x coordinate, y coordinate, and the time axis. So if you just take the 1 through the x coordinate number of pixels, 1 through the y coordinate number of pixels, and 1 through the time, then that Cartesian product gives you the video, and a simple nonlinear operator on that produces the video of the bouncing ball. So in particular, if the ball is stationary, then the operator is very easy. It's just, you have a ball, and the same frame is being repeated. So if you stack these frames together, you get a 3D map where the map looks like a cylinder. So the cylinder is a simple PTF that describes the video of a stationary ball. If the ball is bouncing, then it is a union of PTFs, because when you bounce, one bounce of the ball is essentially taking the cylinder and twisting it into a parabolic shape, where the axis of the cylinder has been twisted into a parabolic shape. And it's a union of such things. So learning is trying to go in the opposite direction. It's going to looking at the video that is produced and trying to come up with this, reverse this thing. It may not do it in the exact same order. And as I was saying, even for repeated structures, this low-rank products is useful, like in this bird's case, or even the petals of a flower. You just take the encoding, you're probably taking the operator for each petal and you're just changing the orientation. And this gives you a very low-rank structure, simple low-rank structure. And if you recognize this, then even if a petal is missing, you know that there should be a petal there in the right position. So if we can have a method to look at the image and figure out that, okay, there are these encodings of these individual birds, and these encodings are all very similar except that the positions have changed, then it's easier to go backwards and recover such low-rank structures. So one, maybe real events, especially cartoon-like events, can be represented well with the small DAGs of such polynomial threshold functions and low-rank products. And maybe when we are looking at such cartoons, or even real-world things, we are essentially reconstructing these DAGs in our mind that produce these cartoons. And maybe transformers also are just doing exactly that. That is, that transformers. So when we are uncovering the DAG, note that this is like learning, per instance learning. That means we're taking that one image or one video and trying to figure out the circuit or the program or the network of programs which produces this one video, which is a function from XYT to pixel color. So we are not doing learning over images or over videos. We're just learning the network that produces this one image or one video. And maybe transformers, as Ima's talk was also saying, that maybe you can view a transformer layer as exactly fitting as unroll loop of gradient descent to fit this particular input into a simpler network. So we won't be able to prove this generally, but we will be able to show that if you just have an image which is some product of polynomial threshold functions, then you can actually figure out this DAG, the two-layer DAG of sums and products that produce this image. And we'll also show that this can be used to create a table of concepts. And by concepts, I mean shapes. So if you have many images with different shapes in them, different unions of different shapes, then we can actually construct a table so that you will get one entry for different shapes. So here is how we do it. So first, what we show is that, let's start with just polynomial. If you have a polynomial, you could do things like, if it is a smooth polynomial, not a threshold, if the image is actually a smooth function which is output of a polynomial, so let's say it's a grayscale image, you could do something like just fit a polynomial, low-degree polynomial which produces this. But that's cheating because you don't want to do that. You don't have to specifically do that. You might do more standard learning. And indeed, even very simple things work. Like even if I just do a random projection of a polynomial image, that itself is a good encoding of that image. Just from that random projection, you can get back the original image. And the reason is very simple, because images which are actually polynomial maps are exactly, which are low-degree polynomials, exactly have low rank, because they are just union sums of the x squared, x cubed, or small low powers of x and y. So if I just take a random projection of that into a vector which is slightly more than the degree of the polynomial, then that's enough to tell me the coefficients, because the basis functions will actually be almost orthogonal even in this random projection. And the sketch that you get is linear in the original image, and it's linear in the coefficient vector, and you can invert it back to the original image. So this works for polynomials, which are not thresholds, continuous functions, but it doesn't quite work for polynomial threshold functions. You can't take the image of a cylinder or an ellipse and take a random projection of it and then say that somehow from there it's easy to tell back the parameters of the cylinder and the ellipse. And the reason that happens is because it's pretty simple. It's because even if I just take a rectangle, or just take an image with like black on one side, white on one side, and just shift the boundary. As you shift the boundary, if you just do a random projection, then you will actually, random projection to one dimension, you'll actually get a Brownian motion. You'll get a random walk. And if you have few parameters, if you do dimensions projection, then you're actually getting a random walk in d dimensions. So the random projection of such images is not smooth in the latent parameters. The random projections of polynomial images are very smooth in the latent parameters. So you can't just do it to random projection. But never mind, I mean, very simple twists work. You just take thresholded versions of smooth functions. So, so what we prove is that you can train a small circuit of depth 2, which gives you a smooth representation, which we can use to produce smooth representations. And if you take thresholded versions, then you can actually represent those polynomials, and it's easy to train the parameters of the smooth representation. And similarly, you can also deal with unions and intersections of PTFs. And the idea there is to use patches to look at different parts of the images and then try to fit PTFs for each region and then merge them based on similarity. And the sketch size is essentially the number of edges in this unions and intersections. So it's just the total number of edges times the degree of each polynomial for each of the edges or the faces. So here is here is what you do for, let's take a polynomial function. So as I said, just for a smooth polynomial, which is not a threshold, you can just take a random projection, and that is good enough to preserve the original coefficients of the polynomial. But you can also use a different type of projection, which is actually better for threshold functions. And the different kind of projection is just tile it up into some random tiling into such squares, and then just store the average color in each tile. So if you have a constant number of tiles, like maybe 5 by 5, 25 tiles, and you just store the average value, then you just get a 25-dimensional vector for this entire image. And so this is a different type of projection, and this also works for polynomials. And the reason it works is because this is nothing but a smoothing filter. So if you have a few such random tilings and shifts of it, essentially what you're doing is you're doing local smoothing. So it's like a low-pass filter, like a Gaussian smoothing, almost like a Gaussian smoothing. And as long as the original input is smooth, that is, doesn't have high-frequency components, then you have the information about all the information required in this smoothened version of the image, which is exactly this 25-dimensional vector. If you take these 25-dimensional things, vector, and if you take the sign of the value there, then it can be used to produce a threshold function, which has sharp boundaries. And you can train these values so that it gets a better match. So, the sketch that you get by this is not the same as the coefficient vector of the polynomial which produces these, but it is isomorphic to it, in the sense that it is enough to recover the original thing, and it is smooth in the original parameters. So you get these smooth representations, which you will not get if you just do a random projection for sharp images with boundaries. So pictorially, it can be represented in this way. So you're training a single model for just one image. So it's per instance learning. So you have pixel positions, and you want to predict the color. Let's say it's monochromatic now. So you're predicting the gray value, the grayscale color. And you're doing this tiling, which means it's like an LSH, locality sensitive bucketing. But just think of it as tiling for now. So you're mapping every pixel position to some bucket or a few buckets, and you're storing the average color there. And to predict the value, you just take the average of the few buckets it went to. And this is already good enough for low frequency images. Because for low frequency images, the averaging doesn't change the thing too much. But you can also train the values in this rather than just taking the average. So, for example, if you just take the averages, that you can view that as a first iteration, and then you just look at the delta, that means the error in the prediction, and you just keep correcting the values in there. So if you keep doing this, it's like training the values in there, and we know that there exists the right values here to produce any low degree polynomial. So, this is like training this network to exactly match the image. And instead of just predicting the average, if you predict the sign of the average, then you can represent polynomial threshold functions. So, and we know again that there exists some values in here which will exactly map to the ellipse, and it's a convex function because you're only training you're only outputting a signed version of a linear function. And if you use cross entropy, you can just exactly fit it and learn it. So notice the difference between, notice the similarity between convolutional networks and this. So here I was doing per instance learning, but if you look at this averaging and tiling, it looks a little bit like CNNs. So CNNs also do this average pooling. And if you unroll the iterations of this power iteration to change the values within each, to keep updating values, maybe the CNN is doing something similar. So the same idea can be used for intersections of PTFs. So that what I did before was working for one PTF like an ellipse. But if you have multiple PTFs, like an intersection of PTFs like this rectangle, again you can apply the technique. The sketch size that you get is going to be proportional to the number of edges and the degree of the polynomial in each edge. And the idea is, again, just break it up into tiles and take a few random tilings, and now learn a sketch within each tile. So if some tiles will have two edges, will have two polynomials in it, but most of the tiles will be pure. That is, they'll only have at most one edge or no edge. So for those tiles, you can get very clean representations. For these corner tiles, which have both of them, you may not get a clean representation using a small size sketch. So, but you just recurse. Whenever you get a sketch which doesn't easily recover this thing, then you break it into smaller tiles, further smaller tiles, and keep increasing things. So you get like a tree-like representation of this rectangle where you're constantly expanding the corners, and once you go to log-in depth, then you get a pretty good representation sketch. And this sketch is also like progressive. Like you can make it approximately reconstruct the rectangle by just using the initial few layers, and they get finer and finer with more layers. And another thing you do is you don't need to keep this as a tree. You can actually convert this into a DAG. Why? Because the sketches of these two patches are the same, or they're going to be very similar, because they're using the same polynomial. They're constructed using the same polynomial. So you can merge sketches which are similar. So the way you merge is that you use another hash table, locality sensitive hash table, that stores these sketches. And when two sketches are the same, they'll just point back to the same entry in the table. So you just replace the sketch by a pointer to the table. So that converts this into a DAG-like structure. So this exactly gives you a DAG which generated this with this rectangle. And it's producing variable size encodings for different regions. So it's producing a variable size encoding for it's using very small sketches for the pure black and white patches. It's using a slightly more complicated for this one, and even more complicated for this one. So that is for learning one image or reconstructing one image. Now let's see how to learn the concept of shape. Like how do you represent the concept of all ellipses or all rectangles? So this point is a little subtle. So just pay attention and ask me if you have any questions. So the important thing to note is that if you look at things in coefficient space, that means you take an image of a shape and you look at it in coefficient space. So look at ellipses. If you could convert the image of an ellipse back into its coefficient vector, so let's say you write it as just ax squared plus bx squared minus some constant, then the concept of ellipse is nothing but a region in this coefficient space. So if you take degree 2 functions, degree 2 polynomials, then there are like 6 coefficients. But let's say for simplicity, we're just looking at the x squared and y squared coefficients. Then the ellipse is nothing but a rectangular region in the top right quadrant. And hyperbolas will just be another rectangular region here. So the concept of an ellipse is nothing but a specific image or decomposition of this. So you look at this set of points, you take all the different images of different shapes, you put them in sketch space. Here it is only 2-dimensional. And what you will get is one image. But this is a meta image, it's not a visible image. It's an image that you draw by taking sketches of individual images and populating it as pixel values in sketch space. And what you get is this one big image, and a shape is nothing but different regions in this meta image. So ellipse is nothing but a rectangle or an intersection of PTFs, and hyperbolas will be another thing, and so on and so forth. So you can just apply the same algorithm again. So that means whatever algorithm you were doing to study one image and describe it in terms of regions or intersections or unions of regions, you just do that again in the sketch space. You take all the sketches, put them into a map, and they have a low dimensional structure, and you just apply the same algorithm again and connected regions in here is actually a concept. And in fact, you don't even need labeled data. Like if these regions are disjoint, I don't even need to label that these are ellipses. I can just say that, okay, I see these distinct regions. Each of them has a continuous structure, has a nice intersection of PTFs. And I can just give them some new names, and these are my concepts. And there you get pretty robust definitions because maybe ellipses are all, you can easily distinguish between ellipses and hyperbolas because in hyperbolas, the B will be strictly far from negative and ellipse will be strictly positive. So in this representation, things are very far apart in the sketch space. So I think I'm out of time. The main thing I want to point out is that we are far from this pictorial theoretical structure that we see out of this thought experiment. And the whole notion of MOEs and knowledge tables can be thought of as an initial step in this direction, but I think we have a long ways to go. And we need to go a long ways in terms of adding the right ingredients into today's transformer mixture of exposed architecture with tables to get there to create nice DAG-like representations. And at least maybe we can hope for that in cartoon-like synthetic inputs. So that concludes the talk, and here are some references. Happy to take any last few questions.
Right. Thank you, Rina. We already get a lot of questions along the way. Do we have any left questions? Please.
So I was wondering how do the results extend when you have noisy images? So for instance, in all these examples, your images that you are working with are exactly generated from some underlying DAG. What if you now have, let's say, salt and pepper noise in the images, or let's say in the minions example, you have, let's say, a few pixels that are not rendered properly, given the actual DAG.
So if you have random noise, then it's relatively easy, right? Because if you take an ellipse,
but then you have to reconstruct it exactly, right? So doesn't the sketch size blow up?
No, because you don't want to reconstruct it. Like, I don't think we would be reconstructed exactly. We would only be, like, you would keep reconstructing it, and if the, beyond a certain point, if it becomes too big, then you drop at that point. So for a noisy rectangle, you can very easily reconstruct it in terms of up to some high level of accuracy, which is these 4 edges. But to get every pixel right, you will need a very big sketch, so you just drop it at that point. So, or even if you do reconstruct it, remember when I was saying that you combine objects, when you combine objects, you keep sketches of small size. So high level details are always downweighted in that sense.
I see. Thank you.
Is there any other question? If not, Rina, I'm wondering, so if you want to offer some take-home messages for people working on transformers or MOE those days, what should be learned as a practical design choices from those very interesting findings?
So you're asking for what would be specific things to include in today's MOE?
In today's MOE, if someone want to improve it for the next step.
Yeah, I think there are quite a few, 2 or 3 things. One is you want to have a more intelligent routing module, like not just a softmax-based thing, but the routing module itself should have its own tables, routing tables, decision trees, that kind of thing. Another is you should not think of MOE as separate from knowledge tables, table of entities, but they're the same things and they should be co-located. Another thing is you want to have a graph across these modules and entities based on co-occurrence, or if you're frequently routing to one module for another module, another one, then you can track these paths based on frequency. And you find common subgraphs and make them into like a higher level module, subroutine. So I think that's 3 or 4 things which I think are very important.
Okay. Is Google already trying out some of those ideas?
Well, let's see.
All right, thank you.